Okay, so I think this should be recorded right now. So let me go notability. Okay, let's get started. Can everyone see my screen? Someone just say yeah.
Yeah.
Okay,
Yeah.
so today we'll go over rash, but before that, let me announce my office hours. So from what I see, if you look at the syllabus, so I go write syllabus. So homework is assigned Fridays by your professor. So not by me. So by professor, and they're due on quiz days. So so I mean it's convenient, right? You upload the quiz and homework like at the same time, pretty much. So basically, homework will be due on quiz days, and quiz days if you look at the syllabus, there's a calendar, and the calendar basically tells you everything. So the quizzes will be Thursdays, and it starts April 8th. So I guess, I guess next week. So okay, so my office hours will be Tuesday, Thursday. So just before this. So yeah. So, and then or by appointment, I guess. So again, like, I know some of you this time is probably not a good time in like other time zones. So, okay. Any questions before we start? So hopefully you had practice uploading quiz 0. So again, I'm not grading it, but it's good practice to upload PDFs. So let's start. So but last time we went over the natural numbers, right? This is like 1, 2, 3. And basically the naturals are used in induction. So the next step is integers. So basically the point of the beginning of this book is to like literally construct the real numbers. So just think of yourself as some like person in like way back then where you just discovered what numbers are. So this is basically, it goes both ways, right? Like -1, 0, 1, so on and so forth. And then people, discovered rational numbers from dividing, right? When you introduce division, you realize the rational numbers are like P over Q, where PQ is in Z and Q is not 0, right? So, and then, came like, I know I'm saying this like a story, but it pretty much is. So came like the study of like equations, right? So people realize that, like, for example, like x squared minus 2 equals 0, like they realize the solution to this is not rational. So basically they're like, hey, there are numbers that are, there's more numbers out there. So basically, I mean, the way people figure this out is, like it's not. I mean, there is rational root, the rational, what do they call it, zero theorem, root theorem. So, but basically, back then they, if you just graph this, you basically you're trying to approximate these two roots, and they basically couldn't get an approximation that's rational. So there's like a way to do with like rulers and like protractors or something like that. So like that gives you like it's rational, but in this case they couldn't. So they hypothesized it's not rational, and it turns out it's not. But let me just definition algebraic numbers. Yeah, let me just write out the whole word. So algebraic numbers. So basically, they are roots of some polynomial equation, right? So n minus 1. Yeah. So, for example, the root of you know, the equation above is an algebraic number. So we normally denote it by root 2, right? But I mean, this just means by the, you know, root of x squared minus 2 equals 0, right? Or if I write root, I don't need this. So, you know, because I mean, all of you know root 2 is like, you know, if you use a calculator, it's 1.41, blah, 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 right? But, you know, but by definition, this root 2 is just a symbol. It's just some root of this thing. And then negative of it is the other root. So here comes the rational root. I call it zeros. I don't know what the book calls it. I call it root or zeros. They mean the same thing, right? A root is like a zero of a polynomial. So suppose C0 to Cn is in Z and R is in Q. Satisfy. So basically, if you have a rational solution that satisfies a polynomial equation, there are some conditions on it. So then, you know, well, first off, we could always write, hopefully you all know what I mean by this. So by reduced, so basically what I mean is if C over D is like 2 over 4, right? We write 1/2, right? So that's what I mean by reduced. So like if you want to be pedantic, GCD of CD is 1, right? This is the greatest common divisor, right? So they're pretty.
Professor?
Yes.
Does it say R naught for the last term on your formula there?
Well, sorry. It should be C naught.
Oh, okay, gotcha. Thank you.
Yeah. So basically, when I write reduce, just think, you know, instead of 2/4, I mean like 1/2. So here, then we get C divides C naught and D divides Cn, right? So from here, we immediately see root 2 is not a rational number because root 2 is what? By definition, it's a root of x squared minus 2, right? If root, so we do just prove it, right? If root 2 was in Q.
Fuck, no! Oh, yeah.
That's fine. If there's a background noise, maybe just mute yourself. So root 2, if root 2 is in Q, then what does that mean, right? Root 2 is equal to C over D, and we could write it in reduced form, right? And what does the theorem say? It says C must divide what? What is C naught? C naught is the constant term. So and C divides the constant term, which is 2, and D divides the, what is Cn? Cn's the leading term, right, of the highest degree. So our highest degree is x squared, right? And the leading term is 1, right? So basically you get C is what? Plus minus 2 plus minus 1, and D is plus minus 1, right? So C over D can be what? It could be plus minus 2 or plus minus 1, right? And basically you just plug it in, right, and check, right? So 2 squared minus 2 is not 0. Negative 2 squared minus 2 is not 0. Negative 1 squared minus 2 is not 0. And 1 squared minus 2 is not 0, right? So, and we get a contradiction, right? Because we said root 2 was a root, and if it was, and we assumed it was rational, then it has to be either plus minus 2 or plus minus 1, but none of these give 0, right? So root 2 cannot be rational. So root 2 is not in Q. Okay, does everyone understand how this works? So it's pretty simple. It's just, you're just checking whether something fits an equation or not. Okay, So let's go over to harder examples and maybe a trick I'll show you. So this, I think this is part of the exercise, but you know, let's do this. Yeah. So before, I mean, root 2, it was easy to see what the polynomial, I mean, what the polynomial was, right? I mean, but it gets harder if you know, start introducing multiple square roots. So here, the trick is to always set like alpha to be what you want, and then start squaring, right? Start squaring and getting rid of those square roots. So let's get rid of the square root on the outside. So we have alpha squared is 2 plus root 2. Now I only have one square root left. And how do I get rid of it? Well, I need a square, right? I can't square right now because the FOIL law will still give me a square root, right? If I square 2 plus root 2, that's not going to work, right? Because I'll still have a square root after I square it. So let's move the 2 to the other side. And now I can square both sides. And now you see that all the square roots are gone, right? So instead of writing square, I'll write, you know, this twice. And this is what? Alpha to the 4th minus 4 alpha squared plus 4. And this is 2, right? So let's subtract. So this is, but this exactly means what? This means if I plug in alpha is root, by definition, is root of x to the 4th minus 4x squared plus 2, right? Oh, I always write the equal 0. So let me, right? Because if I plug in alpha from above, you see that it's 0. So again, you can apply rational root theorem, right? So what you're going to notice is it's nice if the, you know, if the constant term and the leading term is small, right? Like we don't care about that 4. I mean, rational 0 theorem, I mean, I guess for calculations, it might make your calculation longer. But the number of choices, right? Here, the plus minus 2 plus minus 1, therefore we only have like 2 choices, right? So, but like if, for example, instead of a 2 here, we had like a, you know, 12, we would have to check plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, and plus minus 12, right? That's like a lot. So it's nice if like your constant term and leading term is small. So here, right, so if alpha was in Q, so again, assumed by contradiction, alpha is C over D reduced, where C divides 2 and D, and again, I guess the same thing here. D is plus minus 2 plus minus 1, right? So again, so C over D is what, if you just think of all the possible combinations, it's this, right? So now you just plug it in. So 2 to the 4th minus 4. So this should be 2, right, which is not 0. Negative 2 gives the same thing because we always raise something to the even power. So, and if you plug in 1, well, 1 to the 4th minus 4 times 1 squared plus 2. What is that? That's negative 1, right? Not 0. And similarly, this, right? So you see, it gets pretty, but so this, let me write maybe, let me write this. Let me just write this is method 1. So let me show you another method. It uses the fact that we previously showed root 2 was not rational, right? So remember what was the method 2? What was alpha? Alpha was root 2 plus root 2, right? If I remember correctly, yes. So alpha is root 2 plus root 2. So one thing you're gonna notice is alpha squared. If alpha is rational, if alpha is c over d, right? So c over d equals root 2 plus root 2. We can get a contradiction another way. We could square both sides still. So d squared equals 2 plus root 2. And if you subtract 2, what you're going to get is the thing on the left is still rational, right? I mean, if you don't believe me, it's this, right? Over d squared, right? This thing is still rational, right? I mean, the top is some combination of integers. The bottom is an integer, right? So it's still rational. So this is, let me write it better. This belongs in Q. And we showed before that root 2 was not rational. So we get a contradiction, right? So this cannot happen. So I mean, either way you want to do it. I find this easier. So if that works for you, then yeah. Okay. Any questions so far?
I had a question. So on the, if you scroll up, you stated that if alpha is in Q and alpha equals C over D, where C divides 2 and D divides 1, where did you get that, like C divides 2, D divides 1 part?
So what does rational zero theorem say? It says if you are a root and you're rational, your C divides the constant term here, and your D divides the leading term. The leading term here is 1. So.
Oh, I see. Okay. So we're going to be looking at the last constant term and the first leading term.
Right. Yeah.
Okay. Gotcha. Thank you.
So if you go back, right, C divides C0. C0 is the constant term, right? And D divides C. Cn is the leading term.
Oh, okay. Okay. I see now.
Okay. I maybe I get your confused. So we assume Cn is not 0. Yeah.
Right.
I mean, you can always write, like, you know, for example, like if like x squared minus 2 as like 0 x3, you know, but I mean, but you can always reduce to like your leading term being not 0. So
Right. Okay. Gotcha.
yeah.
Thank you.
Okay. So, but that actually, you know, gives us, I mean, we can actually generalize this to basically solving everything. So let's consider if, do I want to use alpha? Yeah, if alpha is irrational. So maybe they haven't defined. So by definition, alpha being irrational means not rational. Yeah. So beta is rational. Basically, you know, let's consider, you know, all possible operations, right? So let's consider alpha plus beta, alpha squared, I don't know, alpha beta, making these up. So beta over alpha and root alpha, and let's do, let's say root beta, right? So are these rational, irrational, or I mean, I'll write depends. Yeah, it could, depends means like it could be either, right? So the first one, what do you all think?
Irrational?
Yeah, it's gonna be irrational, right? Because if we assume it, so the way you do this is assume alpha plus beta was rational, then alpha plus beta is C over D, right? Sadly, I mean, beta was also rational, right? So, and so alpha plus, so I don't know, what letter should I use? R over S? So we could write beta as like R over S, right? And you could clearly see that that means alpha had to be rational, right? Because alpha is, if you just combine CS minus RD over DS, right? This is in Q. Sorry, in Q. And that's a contradiction, right? Because we said alpha, we assumed alpha was irrational here. Okay, so that proves one. Okay, what about alpha squared? Any ideas?
Depends.
Depends, yeah.
Yeah, so in fact, we went over the two examples where it depends. So the first one was root 2, right? If alpha is root 2 squared is 2. That's an integer, which is certainly in Q, right? Because you could write 2 as 2 over 1. So, but also the previous example I gave, like square root of this, right, is what? If I square this, it's 2 plus root 2. And we know this is all right, IRR for I'll just irrational. And this is rational, right? And from step 1 or step I, right, we alpha, we said that this was not in Q, right? And I mean, rational plus irrational, that's basically part I, right? We said that it's not rational. So this one's depend, right? Let me box the answers. So this one is irrational. Okay, now what about alpha beta? I guess, yes.
Would that be irrational as well?
Yeah, I guess you know, people don't really consider the case beta 0. If beta 0, it's actually rational. So let me just write, if beta not equal to 0, alpha beta is irrational, right? So, I mean, that's clear because if if beta is not 0, it's like R over S, and if this was C over D, you just cross multiply. I mean, you just multiply by reciprocal. Sorry, right? And this would mean alpha is in Q, right? So basically, I don't know. I mean, maybe it'll be faster to just prove all of these and then use it on your homework instead of using rational 0 theorem. But I don't know which way is faster. Depends how much homework questions you have on this section. So part 4. So the answer here is and if beta is 0, well, alpha times beta is 0, right? So alpha beta is 0, so rational. So IV, so again, beta divided by alpha. So again, let me just exclude if beta is 0, beta over alpha is 0, which is in Q. Yeah. So let's consider beta not 0. And I'm implicitly assuming, first off, alpha can't be 0, right? Because 0 is not irrational. So we have no issues with dividing by 0. So here, I mean, it's the same game, right? You just say this is C over D. And if you just cross multiply, you get alpha C equals dr over S. So alpha is dr over SC, right? So this is in Q. So if beta over alpha was in Q, then again we get a contradiction, right? So this we get irrational. Box this. Okay, so is that all? Oh, there's two more. So v square root of alpha. What about that?
Would that also be irrational?
Yeah, so I mean, if you want to show something's irrational, the best way is to assume it's rational and then get a contradiction, right? So if root alpha is c over d, then alpha squared, sorry, not alpha squared. If I square both sides, alpha is c squared over d squared, right? And that's in Q. And I think this one should be clear, right? Root beta. So root beta is going to be what?
Sorry, can you go back to v really quickly? And how is it a contradiction that c squared over d squared is in the rational numbers?
The contradiction is alpha is in the rational.
So are we assuming that it is irrational first?
No,
oh, I see.
it's
Okay,
given.
so
Yeah,
yeah,
it's given alpha is irrational.
Okay,
yeah.
I got you. Okay, thank you.
Yeah. So the reason I'm going over this is because on your homework, what they basically do is, they just keep taking operations, right? Like square roots of square roots, or like square roots and then sum and then square roots. So if you have these rules, you just apply it, right? So, or you don't need to do this if you want to. I mean, this seems faster if like you have to. It's better than checking many. I guess it depends, right? If rational zero theorem is faster if the constant term and the leading coefficient is like small, right? But if it has a lot of factors, you don't want to check every single one, right? Okay, so root beta is what?
Would that depend on what beta was?
Yes, I mean, easy example, root 4 is 2, right? But, root 2 is not in Q, yeah? So this is depends. Yeah, so I encourage you, so as practice, try, alpha irrational, beta irrational. Yeah, so you could try that out for yourself. So before, I didn't copy it down, but let me go to Kenneth Ross. So, where is Kenneth Ross? Okay, so let's go over some more questions. So you see, like, if you see my screen right now, 2.8, it looks really nasty, right? But if you look at it, what are the only roots you have to check? What are the
plus or minus 1?
Yeah, it's plus or minus 1, right? So now you see what I mean. Like it's really easy. It doesn't matter what's in the middle. I guess it might take some more time to calculate, but like the number of things you have to check only depends on the constant and the leading term. So like it's really bad if like that 1 was like a 12 or something. But yeah, so let's do maybe 2.4 even numbers, since I don't know if you all know, but there's sort of like answers in the back of the book for the odds or hints. So cube root of 5 minus root 3. So cube root of 5. So we're doing cube roots now, but the idea is the same. So again, what should we do? So we have two ways, right? I told you the first way is you can show root 3 is not rational. So let me write it, do it from here, method 1. So root 3 is not in Q, right? Because it's a root of x squared minus 3 equals 0. But if it was rational, then the roots are what? The leading terms 3 and the constant terms -3. And so if root 3 is C over D reduced. Then C divides -3 and D divides 1, right? So C over D is plus minus 3. The minus sign doesn't matter, so plus minus 1. And you could easily plug it in and check, right? So sorry, not 0. And -3 squared minus 3. So this is easy to check, right? So you get that √3 is not in Q. But then if you let alpha be cube root of 5 minus √3, so you get alpha cubed. So let me just write this. So now you assume by contradiction, suppose alpha is, I don't know, you see R over S, right? Then R over S equals cube root of 5 minus √3. R cubed over S cubed is 5 minus √3. And you must subtract 5. So okay, I'm gonna skip a step. So I'm gonna subtract 5 and divide by -1, yeah, to get rid of that negative sign. So it's 5 minus, yeah. So from here you get 5. Sorry, my 5s look like S's. S cubed minus R cubed. But in your case, you could see that this means √3 was rational, right? So the left-hand side belongs to Q. So you get a contradiction. So this way, you're still using rational zero theorem, but you're using it on √3, right? And then we get a contradiction. The second part, the second way is to actually use it on the whole thing. So I don't know how nasty this will be, but let's try it. So you get alpha cubed is 5 minus √3, and then subtract 5. And the negative doesn't matter. If we square both sides, go away. So, oh yeah, this will be maybe it's not that bad. It's because it's square. So I get 3. Oh, maybe let's see. So alpha q or alpha to 6 minus 10 alpha cubed plus 25 is 3, right? So you see, you get this, right? Minus plus 22 is 0. So alpha is a root of this. So alpha is a root of x to the 6 minus 10x cubed plus 22 is 0. So here, what are the factors you have to check? So
plus or minus 5 and then plus or minus 1. Oh wait, sorry. No, it would be plus or minus 1 and then it would be plus or minus 22.
No, this is why the previous method was better. So if alpha was C over D reduced, right? C divides 22, D divides 1. So C, you see there's already 8 options, right? You have plus minus 22, plus minus 1, plus minus 2, plus minus 11. So, and then D is plus minus 1, right? So your possible values, so you basically have to plug in 8 different values, right? And you see that's very bad. So I mean, it should be none of these are 0. Yeah. So let me just write 10. Yes. And so none of these should be 0. Yeah. But you would have to check that. So I'll leave that to you. So.
Oh wait, how you get 8 values? How you get 8 values?
So C must divide 22, right? What numbers divide 22?
22.
And what else?
1, 2. Oh, I got it.
Yeah. So yeah, you see, even if even when there's 4 factors, you have to double it, right? Because you have the plus minus. So it's already just 4 factors already. You have to check 8 different values, right? So I'm gonna, yeah. So let me just write this down. So you see this is not very ideal, right? Not 0.
So this was the second method?
Yeah. Second method is check all these values is not 0, right?
Gotcha.
Yeah, so method 2. You're still using rational zero theorem, but you're using it on 2 different, polynomials. So here you're using it on the whole thing. So right, you have to write 8 different times. And you see like the number 12 already makes things really bad, right? Because the number 12 has a lot of factors, right? You have 2, 3, 4, 6, 1, and 12, right? And then you have to double that with the plus minus. So I suggest you try to find ways to use something like method 1, right? So that would be more ideal. Yeah.
In method 1, the contradiction, it's a contradiction because the left-hand side is in Q, but the right-hand side isn't. Is that the reason why it's a contradiction?
Which part? So
the very last line. So right there, you have your fraction is equal to root 3.
yeah, so root 3 is not rational because we just proved it here.
Oh, I see. Okay.
Right, we just that was the whole point of doing the first part. So the first part right here was to show root 3 was not in Q.
Oh, okay, I see.
Yeah, so the reason method 1's better is because we're still using rational 0, but we're using it on root 3 instead of the whole number.
Okay, I see.
Yeah. Yeah, I suggest you try to find ways to do this instead of like checking like 8 different values. So okay, so I think that's all I have for today because I think there's not much that's covered in this section. So any questions?
Just to double check, do we have a quiz due tonight by 12?
Tonight by 12? No. So again, it's all based on the calendar. So your first quiz is like next week Thursday.
Oh, okay, gotcha.
Yeah. So I'll tell you like on Tuesday what the quiz will be on. Yeah.
Okay, gotcha. Thank you.
Yeah. You do have quiz 0, so that one's not graded, but
Right.
please try uploading.
Gotcha.
Today's video will be uploaded.
Yeah, I'll send you the link to it. I think I know how it's recording right now. So
Okay, thank you.
yeah. So okay, any other questions? Okay. All right. Thank you.